Introduction to TCP Adjust MSS. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this presentation, we are going to explore one of the most important yet often overlooked TCP optimization techniques called TCP Adjust MSS, or Maximum Segment Size Adjustment. This technology is fundamental to ensuring reliable data transmission across networks that contain tunnels, VPNs, or any encapsulation that reduces the effective packet size. Understanding MSS adjustment is critical for network engineers because it directly impacts application performance, user experience, and troubleshooting capabilities. When MSS is not properly configured, users experience symptoms like stalled connections, timeouts, and slow file transfers that can be extremely difficult to diagnose without understanding the underlying mechanics. Throughout this presentation, we will cover the theoretical foundations of how MSS works within the TCP protocol, examine the relationship between MSS and MTU, explore common problems that arise when these values are misconfigured, and learn practical implementation techniques across multiple platforms including Cisco routers, Linux systems, and cloud environments. By the end of this presentation, you will have a comprehensive understanding of when and how to implement TCP MSS adjustment to solve fragmentation-related connectivity issues in your network infrastructure. TCP three-way handshake and MSS negotiation. Now that we understand the relationship between MTU and MSS, let us examine how MSS values are actually communicated and agreed upon between two hosts. This negotiation happens during the TCP three-way handshake, which is the connection establishment phase of TCP. The sequence diagram illustrates the complete MSS negotiation process between a client and a server. Let me walk through each step of this critical exchange. The process begins when the client initiates a TCP connection by sending a SYN packet to the server. Along with the SYN flag, the client includes an MSS option in the TCP header that advertises the maximum segment size the client is willing to receive. In our example, the client advertises MSS equals 1460. This value tells the server not to send any TCP segments larger than 1460 bytes of data to this client. The server responds with a SYN ACK packet. This packet acknowledges the client's SYN and also sends the server's own SYN to complete the bidirectional connection setup. Crucially, the server also includes its own MSS option. In our example, the server advertises MSS equals 1460 as well. This tells the client the maximum segment size the server can receive. The client completes the handshake by sending an ACK packet to acknowledge the server's SYN. At this point, the connection is established and both sides know the maximum segment size they can send to the other. There is an important note in the diagram that highlights a critical concept. Each side independently advertises its receive capability. This means the two MSS values do not need to match. The client could advertise 1460 while the server advertises 1380 if it sits behind a tunnel. Each host then uses the MSS advertised by its peer when sending data. The final step shows the data exchange phase where both sides send TCP segments that respect the negotiated MSS values. The actual data segments will never exceed the MSS that was advertised by the receiving host, ensuring that the receiver can process the incoming packets without fragmentation issues. Understanding this negotiation process is essential because TCP MSS adjustment works by modifying these MSS values as packets traverse network devices like routers and firewalls. Path MTU discovery limitations. You might wonder why we need TCP MSS adjustment when Path MTU discovery, or PMTUD, exists to solve exactly this problem. PMTUD is indeed designed to discover the smallest MTU along a network path and adjust packet sizes accordingly. However, in practice, PMTUD often fails due to several common network configurations and security practices. The diagram illustrates how path maximum transmission unit discovery is supposed to work and the points where it commonly fails. Let me trace through the entire flow. The process starts at the sender, which transmits a packet with the DF flag set. The DF flag, which stands for Do Not Fragment, tells intermediate routers that they must not fragment this packet. If the packet is too large for any link, it should be dropped instead of fragmented. The packet travels through router 1, which has an MTU of 1500. Since the packet fits within this MTU, router 1 forwards it normally to the next hop. Next, the packet reaches router 2, which also has a 1500 byte MTU and forwards the packet without issue. The packet is still within the acceptable size for these links. The packet then arrives at a VPN tunnel, which adds encapsulation headers. After encapsulation, the packet now exceeds the effective MTU of the tunnel. The VPN device determines that the packet is too large and must be dropped according to the DF flag rules. When the packet is dropped, the VPN tunnel is supposed to send an ICMP fragmentation needed message back to the original sender. This ICMP message contains the MTU of the link that caused the drop, allowing the sender to reduce its packet size and retry. This ICMP Type 3 Code 4 message is essential for PMTUD to function. However, here is where the critical failure occurs. The ICMP message must traverse a firewall to reach the sender. Many firewalls block ICMP messages as a security measure, or they may have rules that inadvertently filter these specific ICMP types. The diagram shows the firewall blocking the ICMP message with a large X. Without the ICMP message reaching the sender, path MTU discovery fails completely. The sender never learns that its packets are too large, so it continues sending packets at the same size. These packets continue to be dropped at the VPN tunnel, and the connection appears to stall or time out. This creates a black hole where large packets disappear without any indication to the sender. This PMTUD black hole problem is extremely common in enterprise networks and is the primary reason TCP MSS adjustment is so valuable. By proactively reducing the MSS, we eliminate the dependency on PMTUD entirely. Calculating the correct MSS value. One of the most important aspects of implementing TCP MSS adjustment is calculating the correct MSS value to use. Setting this value too high defeats the purpose of clamping, while setting it too low unnecessarily reduces throughput. Let us examine the calculation methodology in detail. The diagram provides a visual representation of how MSS is calculated based on the various header overheads that must be accounted for. Let me walk through each component. We begin with the total MTU of 1500 bytes. This is our starting point and represents the standard Ethernet MTU that most networks support. The first deduction is for the IP header, which is 20 bytes. This is the outer IP header that will exist on the final packet after all encapsulation. Every IP packet requires this header. Next, we must account for the tunnel overhead. This is where the calculation becomes specific to your environment. The tunnel overhead varies depending on the type of tunnel or VPN in use. The diagram shows several common examples. GRE adds 4 bytes. IPsec ESP can add 50 to 57 bytes depending on the encryption algorithm and mode, and IPsec with NAT traversal adds an additional 8 bytes for the UDP encapsulation. You must know exactly what encapsulation your network uses to calculate this correctly. After tunnel overhead, we deduct another 20 bytes for the inner IP header. This is the original IP header of the packet before encapsulation. Both the outer and inner IP headers exist in the encapsulated packet. We then deduct 20 bytes for the TCP header, which contains the port numbers, sequence numbers, and other TCP control information. Finally, we arrive at the MSS value, which is what remains after all headers are accounted for. This represents the maximum amount of application data that can be carried in a single TCP segment while still fitting within the path MTU after encapsulation. The formula shown in the diagram calculates the MSS as 1500-20 tunnel overhead -20-20. For a simple GRE tunnel, this gives us 1500-20-4-20-20, which equals 1436 bytes. For IPsec, the MSS might be as low as 1360 bytes or even lower depending on the specific encryption configuration. As a practical guideline, many network engineers use 1400 as a safe default MSS clamp value because it accommodates most common tunnel types with some margin for safety. Linux IP tables MSS configuration. Linux systems provide MSS clamping capability through IP tables using the TCP MSS target. This approach offers more flexibility than router-based solutions because you can apply very granular matching criteria to determine which packets should have their MSS adjusted. The code block shows several IP tables configurations for TCP MSS adjustment. Let me explain each command thoroughly. The first command demonstrates the most common approach using automatic MSS calculation. The command is IP tables with several parameters. The -t mangle specifies that we are working with the mangle table, which is used for packet alteration operations like MSS modification. The -a forward appends this rule to the forward chain, which processes packets being routed through this Linux system to another destination. The -pTCP specifies that this rule only applies to TCP protocol packets. The TCP flags SYN, or ST-SYN is a critical match condition that identifies TCP SYN packets specifically. This match syntax means we are looking for packets where the SYN flag is set and the ST flag is not set, which identifies connection initiation packets. The JTCP MSS specifies the target action, which invokes the TCP MSS module. The clamp MSS to PMTU option tells the kernel to automatically calculate the appropriate MSS based on the path MTU of the outgoing interface. This is the recommended approach when you want the system to dynamically determine the correct MSS value. The second command shows how to set a specific MSS value instead of using automatic calculation. The structure is the same, but instead of clamp MSS to PMTU, we use set MSS 1400 to explicitly set the MSS to 1400 bytes. This approach is useful when you know the exact MSS value needed for your environment. The third command demonstrates applying MSS clamping to a specific interface using the -o eth0 option. The -o flag specifies the outgoing interface, so this rule only affects packets leaving through eth0. This is useful when you have multiple interfaces and only need MSS adjustment on certain paths. The fourth section shows how to verify the IP tables rules using IP tables space -t mangle space -l space -n space -v. The -l lists all rules, -n shows numeric addresses instead of resolving host names, and -v provides verbose output including packet and byte counters. This allows you to confirm your rules are configured correctly and see how many packets have matched each rule. To make these rules persistent across reboots, you would save them using IP tables save and configure your system to restore them on startup using IP tables restore. Common MSS values reference. Having examined the theory and configuration of TCP MSS adjustment, let us now look at a practical reference table of common MSS values for different network scenarios. This table will help you quickly determine the appropriate MSS setting for your specific environment. The table presents 4 columns. The network scenario describing the type of connection, the MTU showing the effective maximum transmission unit, the recommended MSS value, and the overhead explaining what headers consume the space. The first row covers standard Ethernet, which has an MTU of 15,100 bytes. The recommended MSS is 1460 bytes. The overhead consists of 20 bytes for the IP header and 20 bytes for the TCP header. This is the baseline configuration for networks without any tunneling or encapsulation. The second row addresses GRE tunnel scenarios. The MTU remains 1500 for the underlying network, but the recommended MSS drops to 1436 bytes. The additional overhead includes 4 bytes for the GRE header on top of the standard IP and TCP headers. GRE is a simple encapsulation protocol commonly used for point-to-point tunnels. The third row covers IPsec tunnel mode, which is commonly used for site-to-site VPNs. The recommended MSS is significantly lower at 1360 bytes. This accounts for the IPsec overhead, which includes the ESP header, initialization vector, padding, and authentication trailer. The exact overhead varies based on the encryption algorithm, but 1360 provides a safe margin. The fourth row shows IPsec with NAT traversal, which adds UDP encapsulation to allow IPsec traffic to pass through NAT devices. The recommended MSS drops further to 1352 bytes because NAT-T adds an 8-byte UDP header on top of the standard IPsec overhead. The fifth row addresses PPPoE connections, which are common in DSL and some fiber deployments. PPPoE adds 8 bytes of overhead, reducing the effective MTU to 1492 and the recommended MSS to 1452 bytes. The sixth row shows VXLAN, a network virtualization technology used extensively in data centers and cloud environments. VXLAN adds 50 bytes of overhead including the outer Ethernet, IP, UDP, and VXLAN headers. This results in a recommended MSS of 1410 bytes. The final row covers WireGuard VPN, a modern VPN protocol. WireGuard adds approximately 60 bytes of overhead, resulting in a recommended MSS of 1380 bytes. These values serve as starting points for your configuration. You should always verify the actual overhead in your specific environment and adjust accordingly. Troubleshooting with TCP dump. When you suspect MSS-related issues are causing connectivity problems, the first step is to capture and analyze the TCP handshake. TCP dump is an invaluable tool for this purpose because it allows you to see the actual MSS values being exchanged between hosts. Let me walk through the TCP dump commands and output shown in this slide. The first command captures TCP SYN packets on a specific interface. The TCP dump command is invoked with several important flags. The -i eth0 flag specifies the interface to capture on, which in this case is eth0. You would change this to match your network interface name. The NN flag is actually 2 flags combined. The first N prevents DNS resolution of IP addresses, and the second N prevents port number to service name conversion. This makes the output faster and clearer because you see raw IP addresses and port numbers. The TCP flags bracket portion is a filter expression that examines the TCP flags field within captured packets. The ampersand symbol performs a bitwise an operation, and TCP SYN is a constant representing the SYN flag bit. This filter matches only packets where the SYN flag is set, which includes both SYN packets initiating connections and SYN ACK packets responding to connection requests. The -v flag enables verbose output, which is essential because the MSS option only appears in verbose mode. Without this flag, you would see the packet but not the TCP options including MSS. The example output shows a captured SYN packet. The timestamp and source destination addresses are shown first. The flags S indicates this is a SYN packet. The critical information appears in the options section where you can see MSS 1460. This tells you the client is advertising an MSS of 1460 bytes. The second command shows how to capture to a file for later analysis. The -w capture.pcap flag writes packets to a file named capture.pcap in pcap format. This file can be opened in Wireshark for detailed graphical analysis. The third command demonstrates filtering by host while capturing. Adding host 192.168.1.100 to the filter limits capture to packets involving that specific IP address, which helps reduce noise when troubleshooting specific connection issues. AWS VPC MSS considerations. Amazon Web Services presents unique MSS considerations due to the virtual networking infrastructure as a service that underlies all EC2 instances and VPC networking. Understanding how AWS handles maximum transmission unit and maximum segment size is essential for properly configuring applications and VPN connections in AWS environments. The diagram shows the network architecture for an AWS VPC with various connection types. Let me trace through each path and explain the MSS implications. Starting with the VPC itself, AWS VPCs support a maximum MTU of 9001 bytes when using jumbo frames between instances within the same placement group or VPC. However, the standard MTU for most traffic is 1500 bytes, and this is what you should assume for general connectivity. The Internet Gateway connects the VPC to the public Internet. Traffic passing through the Internet Gateway is limited to 15,100 byte MTU regardless of the internal VPC configuration. This means any instance communicating with the Internet should assume standard Ethernet MTU. The VPN gateway presents the most significant MSS challenge. AWS site-to-site VPN connections use IPsec encapsulation, which adds significant overhead. The diagram shows the VPN gateway connecting to an on-premises network through an IPsec tunnel. The recommended MSS for traffic traversing this VPN is 1379 bytes, which AWS specifically documents as the optimal value for their VPN implementation. The transit gateway is shown connecting multiple VPCs and the VPN. Transit gateway adds its own overhead when routing between attachments. For traffic crossing transit gateway to reach a VPN, you may need to read UCE MSS even further to account for both transit gateway and VPN overhead. Direct Connect provides a dedicated connection to AWS. The Direct Connect connection in the diagram offers more MTU flexibility. With Direct Connect, you can use jumbo frames up to 9001 bytes for the private virtual interface, though traffic that routes to the Internet still faces the 1500 byte limit. The key insight is that AWS does not automatically adjust MSS for VPN traffic. You must configure MSS clamping on your on-premises firewall or router to ensure packets are sized appropriately before entering the VPN tunnel. The recommended approach is to configure your on-premises device to clamp MSS to 1379 bytes for all traffic destined to AWS through the VPN. Google Cloud VPN MSS configuration. Google Cloud Platform offers both classic VPN and HAVPN services for connecting on-premises networks to Google Cloud VPCs. Like other cloud providers, GCP VPN connections introduce IPsec overhead that requires MSS adjustment for optimal performance. The code block demonstrates how to create a Google CP VPN tunnel using the G-Cloud command line tool, along with the necessary on-premises MSS configuration. The first command creates a VPN tunnel in Google Cloud. The G-Cloud Compute VPN tunnels create command is followed by the tunnel name, my tunnel in this example. The peer address parameter specifies the public IP address of your on-premises VPN device that Google Cloud will establish the tunnel with. The shared secret parameter provides the IPsec pre-shared key, similar to Azure and AWS configurations. The IKE version parameter specifies which version of the Internet Key Exchange Protocol to use. Version 2 is recommended for better performance and security, though version 1 is supported for legacy devices. The local traffic selector parameter defines which local networks will be accessible through this tunnel. The value quad 0/0 indicates all traffic, but you would typically specify your VPC CIDR ranges. Similarly, remote traffic selector defines which on-premises networks are reachable, with quad 0/0 allowing all remote networks. The target VPN gateway parameter identifies which Google CP VPN gateway resource this tunnel connects to. You must create the VPN gateway before creating tunnels. The region parameter specifies the Google CP region where the tunnel and gateway exist. Like Azure, Google Cloud VPN does not automatically adjust MSS values. The comment in the code block notes that MSS clamping is required on the on-premises device. Google recommends an MSS of 1360 bytes for their VPN implementations. The second section shows the on-premises router configuration using Cisco iOS syntax. The IPTCP adjust MSS 1360 command is applied to the tunnel interface facing Google Cloud. This ensures all TCP connections traversing the tunnel will negotiate an appropriately sized MSS. The third section demonstrates creating the same tunnel using Terraform, which is a popular infrastructure as a service tool. Palo Alto Firewall MSS configuration. Palo Alto Networks firewalls are widely deployed in enterprise environments and frequently serve as VPN termination points. Palo Alto provides MSS clamping capability through zone protection profiles, which offers granular control over where and how MSS adjustment is applied. The diagram illustrates how MSS clamping integrates with Palo Alto's security architecture. Let me trace through each component. The flow begins with incoming traffic arriving at the Palo Alto firewall. This traffic could be from internal users, remote sites, or external sources depending on your network design. The traffic first encounters the security zone, which is Palo Alto's fundamental network segmentation concept. Each interface on a Palo Alto firewall belongs to a security zone, and policies are written between zones. The zone determines which protection profiles are applied to the traffic. Attached to each zone is a zone protection profile. This profile contains various protection settings including flood protection, reconnaissance protection, and packet-based attack protection. Importantly for our purposes, the zone protection profile is where TCP MSS clamping is configured. Within the zone protection profile, there is a TCP settings section. This section contains multiple TCP-related protections including SYN flood protection, out-of-order packet handling, and MSS adjustment. The diagram highlights the Adjust MSS setting within TCP settings. The MSS clamping component shows the actual MSS value configuration. You specify the maximum MSS value that should be allowed. Any TCP SYN packet with an MSS larger than this value will have its MSS rewritten to match the configured maximum. After MSS adjustment, traffic proceeds through policy evaluation where security policies determine if the traffic is allowed. The MSS modification happens before policy evaluation, ensuring that even allowed traffic has appropriate MSS values. Finally, outgoing traffic leaves the firewall with the adjusted MSS values. The return SYN acknowledge packets are also processed through the same zone protection profile, ensuring both directions of the connection have appropriate MSS settings. Palo Alto MSS CLI configuration. Now let us examine the specific CLI commands and GUI navigation required to configure MSS clamping on Palo Alto firewalls. Palo Alto supports both CLI and web interface configuration, and I will cover both approaches. The code block begins with entering configuration mode using the configure command. This places you in the configuration hierarchy where you can make changes to the firewall settings. The first configuration command creates or modifies a zone protection profile. The command set zone protection profile navigates to the zone protection configuration area. The profile name Tunnel MSS Protection identifies this specific profile. You can name profiles descriptively to indicate their purpose. Within the profile, we navigate to TCP settings, which contains all TCP-related protections. The Adjust Miss option enables MSS clamping, and we follow it with Enable to activate the feature. Then set the size to 1400. This tells the firewall to reduce any MSS value greater than 1400 down to 1400 bytes. After creating the zone protection profile, we must attach it to a zone for it to take effect. The second set command configures the zone itself. The command set network zone navigates to zone configuration, followed by the zone name tunnel zone. This should match an existing zone that you have defined for your tunnel interfaces. The zone configuration includes network profile zone protection profile, which is where we attach protection profiles to zones. The tunnel MSS protection value references the profile we created in the previous command. The commit command saves and activates the configuration. Palo Alto uses a candidate configuration model where changes are staged until committed. The commit makes your changes active on the firewall. The second section shows GUI navigation steps for those who prefer the web interface. The path begins at network in the main menu, then zones to access zone configuration. Selecting your specific zone opens its settings panel. Within the zone settings, you access zone protection profile settings, then either create a new profile or edit an existing one. Under protection, you find TCP settings where the adjust MSS option and its size value can be configured. The verification command show zone protection zone tunnel zone displays the effective configuration for the specified zone, including the MSS adjustment settings. This confirms your configuration is active and shows the current MSS value. IP version 6 MSS considerations. IP version 6 introduces several changes that affect MSS calculation compared to IP version 4. The larger fixed header size, the elimination of router fragmentation, and the different approach to path MTU discovery all impact how you should configure MSS clamping in IP version 6 environments. The diagram illustrates the key differences between IP version 4 and IP version 6 MSS calculation. Let me walk through each aspect. The comparison starts with the header size difference. IPv4 uses a 20-byte header as its minimum size, though options can extend this. IPv6 uses a fixed 40-byte header, which is double the IPv4 minimum. This larger header directly reduces the available MSS for the same MTU. The MSS calculation comparison shows the impact of this header size difference. For IP version 4 with a 1500-byte MTU, the MSS is 1460 bytes, calculated as 1500-20 for IP-20 for TCP. For IP version 6 with the same 1500-byte MTU, the MSS is only 1440 bytes, calculated as 1500-40 for IP version 6-20 for TCP. This 20-byte difference means IP version 6 connections can carry less application data per segment. The fragmentation handling section highlights a critical architectural difference. In IP version 4, any router along the path can fragment packets if they exceed the outgoing link's MTU. IP version 6 eliminates this capability entirely. In IP version 6, only the source host can fragment packets. Intermediate routers must drop oversized packets and send an ICMP version 6 packet too big message back to the source. This fragmentation difference makes path MTU discovery even more critical in IP version 6. The PMTU dependency section shows that IP version 6 relies heavily on ICMP version 6 packet too big messages. If these messages are blocked by firewalls, IP version 6 connections will fail completely for paths with reduced MTU. There is no fallback to router fragmentation like there is in IP version 4. The tunnel overhead section applies the same principles we discussed for IPv4, but with IPv6 header sizes. For a GRE tunnel over IPv6, you must account for 40 bytes outer IPv6 plus 4 bytes GRE plus 40 bytes inner IPv6 plus 20 bytes TCP. This results in significantly more overhead than the IPv4 equivalent. The final section provides recommended MSS values for common IPv6 scenarios. Standard IPv6 should use 1440. GRE over IPv6 should use 1396, accounting for the tunnel overhead. IPsec over IPv6 requires even lower values around 1340 due to the combination of larger headers and encryption overhead. When configuring MSS clamping for IP version 6 traffic, you may need separate routes that match IP version 6 packets specifically. Many platforms allow you to configure different MSS values for IP version 4 and IP version 6 traffic to account for these differences. MSS troubleshooting decision tree. When you encounter connectivity issues that might be MSS related, following a systematic troubleshooting approach helps you quickly identify and resolve the problem. This decision tree provides a structured methodology for diagnosing MSS issues. The diagram presents a flowchart that guides you through the troubleshooting process. Let me explain each decision point and its implications. The process begins with identifying the symptom. Common MSS-related symptoms include connections that establish but then stall when transferring data, small transfers succeeding while large transfers fail, or applications timing out after the initial handshake. The first decision point asks whether the connection completes the TCP handshake. If the handshake fails entirely, the problem is not MSS related since MSS is only relevant after connection establishment. A failed handshake suggests firewall rules, routing issues, or service availability problems. If the handshake succeeds, the next question is whether large data transfers fail. If small data transfers work but large ones fail, this is a classic MSS or MTU problem signature. Small packets fit through the path, but packets near the MSS size are being dropped. The next diagnostic step involves capturing the TCP handshake to examine actual MSS values. You use TCP dump or Wireshark to capture the SYN and SYN-ACK packets. The decision point asks whether the MSS values are appropriate for your path. If both sides advertise 1460 but your path includes a tunnel with only 1400 bytes available, the MSS is too large. If MSS values appear correct, the next check is whether PMTUD is functioning. You can test this by sending large packets with the DF bit set and checking for ICMP responses. If ICMP fragmentation needed messages are not reaching the sender, PMTUD is broken. For broken PMTU discovery, the solution is to implement MSS clamping at the tunnel entry point. This proactively reduces MSS so packets are never larger than the path can handle, eliminating the dependency on PMTU discovery. If MSS clamping is already configured, verify it is actually being applied. Check packet captures after the clamping device to confirm MSS values are being modified. Configuration errors, incorrect interface selection, or packets bypassing the device are common issues. The final branch addresses cases where maximum segment size appears correct and path maximum transmission unit discovery works. In these cases, the issue may be elsewhere in the network. Consider other factors like TCP window size, congestion, or application level issues. This systematic approach ensures you identify the root cause efficiently rather than making random configuration changes that may not address the actual problem. Case study. Site-to-site VPN black hole. Let me share a real-world case study that demonstrates how MSS issues manifest in production environments. This scenario is one of the most common MSS-related problems that network engineers encounter, and understanding it will help you recognize similar issues in your own networks. The diagram illustrates the network topology involved in this case. A corporate headquarters needed to establish connectivity with a remote branch office using an IPsec VPN tunnel over the Internet. The flow begins at the HQ network, which represents the corporate headquarters location. The headquarters operates a standard enterprise network with a 1500-byte MTU. End users access various applications hosted at both locations. The HQ firewall terminates the VPN tunnel on the headquarters side. This firewall was configured with standard IPsec settings but did not have MSS clamping enabled. The firewall connects to the Internet through its WAN interface. The Internet cloud represents the public Internet path between the two sites. All traffic between headquarters and the branch must traverse this path, which maintains a standard 1500-byte MTU throughout. The branch firewall terminates the other end of the IPsec tunnel. Like the HQ firewall, it was not configured with MSS adjustment. The branch network behind it hosts some application servers that headquarters users need to access. The problem manifested as follows. Users could establish connections to branch office servers, and small requests like DNS queries and simple web pages worked fine. However, large file transfers would stall after transferring a small amount of data, and some web applications would hang after login when they tried to load larger pages. The root cause was that TCP connections were negotiating MSS values of 1460 bytes because neither endpoint was aware of the VPN tunnel. When data segments approached this size, the IPsec encapsulation pushed the total packet size above 1500 bytes. The packets were dropped at the tunnel, but ICMP fragmentation needed messages were being blocked by a transit provider's firewall, creating a classic PMTUD black hole. The solution involved configuring MSS clamping on both firewalls. Setting IPTCP adjust MSS 1360 on the tunnel interfaces immediately resolved all connectivity issues. File transfers completed successfully, and web applications loaded normally. Performance impact analysis. A common concern when implementing MSS clamping is whether reducing the MSS will negatively impact network performance. Let us analyze the actual performance implications to understand when MSS reduction matters and when it does not. The diagram illustrates the performance trade-offs associated with different MSS values. Understanding these trade-offs helps you make informed decisions about MSS configuration. The analysis begins with throughput efficiency, which measures how much of each packet is actual application data versus overhead. With MSS 1460, each packet carries 1460 bytes of data with 40 bytes of header overhead, giving approximately 97.3% efficiency. Reducing MSS to 1400 changes this to 1400 bytes of data with the same 40 bytes overhead, dropping efficiency slightly to 97.2%. The key insight is that the efficiency difference between MSS 1460 and MSS 1400 is negligible, less than 1%. Even with MSS 1360 for IPsec tunnels, efficiency remains above 97%. The performance impact of reduced MSS is minimal in most scenarios. The second factor is packets per transfer, which examines how many packets are required to transfer a given amount of data. For a 1 megabyte file transfer, MSS 1460 requires approximately 718 packets while MSS 1400 requires approximately 748 packets. This represents about 4% more packets, which has minimal impact on modern networks. The third consideration is CPU overhead from processing additional packets. More packets means more interrupts and more header processing. However, modern network interface cards and CPUs handle this easily. The difference between 718 and 748 packets is imperceptible in terms of CPU utilization. The critical comparison is reduced MSS versus fragmentation. When packets must be fragmented because MSS is too large, the overhead is dramatically worse. Fragmentation doubles the packet count, requires reassembly at the destination, and risks transfer failure if any fragment is lost. MSS clamping is always preferable to fragmentation. The comparison also considers reduced MSS versus PMTUD failure. When PMTUD fails due to blocked ICMP, connections stall completely. A working connection with slightly reduced MSS is infinitely better than a broken connection with theoretically optimal MSS. The conclusion is clear. The minor efficiency reduction from MSS clamping is an acceptable trade-off for guaranteed connectivity. Always implement MSS clamping when tunnels or encapsulation are present, even if you believe PMTUD should work. SD-WAN MSS considerations. Software-defined WAN solutions add another layer of complexity to MSS management. SD-WAN platforms typically use overlay tunnels to connect sites, and these tunnels introduce encapsulation overhead that must be accounted for in MSS configuration. The diagram illustrates a typical SD-WAN deployment and the multiple layers of encapsulation that can affect MSS. Let me trace through the architecture. The SD-WAN fabric represents the overlay network created by the SD-WAN solution. This fabric provides intelligent routing, application awareness, and automated failover across multiple transport links. Each site has an SD-WAN edge device. The diagram shows 3 sites: headquarters, branch 1, and branch 2. Each edge device terminates the SD-WAN tunnels and provides local network connectivity. The transport links connect the sites. SD-WAN typically uses multiple transport types for redundancy and cost optimization. The diagram shows MPLS, Internet, and LTE as available transports. Each transport may have different MTU characteristics. The SD-WAN overlay tunnel is where encapsulation occurs. Most SD-WAN solutions use proprietary or standard tunnel protocols like IPsec, GRE, or VXLAN to create the overlay. This encapsulation adds 40 to 80 bytes of overhead depending on the specific implementation. The challenge is that SD-WAN encapsulation stacks on top of any underlying transport encapsulation. If the Internet transport uses an IPsec VPN to a cloud provider, and the SD-WAN adds its own overlay tunnel, the total overhead can exceed 100 bytes. Most SD-WAN solutions handle MSS adjustment automatically. The SD-WAN edge devices are aware of their tunnel overhead and clamp MSS for traffic entering the overlay. However, you should verify this is configured correctly and understand the values being used. The verification step involves checking your SD-WAN platform's configuration for MSS settings. Vendors like Cisco Viptela, VMware VeloCloud, Silver Peak, and Fortinet all provide MSS configuration options. The default values are usually appropriate, but complex deployments may require tuning. Special attention is needed when SD-WAN connects to cloud environments. If your SD-WAN edge in AWS or Azure uses both the SD-WAN overlay and a cloud VPN, you must ensure message size segment accounts for both layers of encapsulation. This might require values as low as 1300 bytes in some configurations. Automating MSS configuration. In modern infrastructure environments, manual MSS configuration does not scale. Network automation tools and infrastructure as a code approaches allow you to manage MSS settings consistently across large numbers of devices. Let me show you several automation approaches. The code block demonstrates automation examples for different platforms. The first section shows an Ansible playbook for configuring Cisco iOS devices. The playbook begins with standard Ansible structure. The name field describes the playbook purpose. The hosts field specifies which inventory group to target, in this case Cisco routers. The gather facts setting is disabled since we do not need system facts for this task. The task section contains the actual configuration work. The first task uses the cisco.ios.ios_config module, which is the standard module for configuring Cisco iOS devices. The line's parameter specifies the configuration commands to apply. Here we are setting IP TCP adjust MSS 1400. The parent's parameter specifies the configuration hierarchy. The command must be applied within interface gigabit Ethernet 0/0, so we specify that as the parent context. This ensures Ansible enters the correct configuration mode before applying the MSS command. The save when parameter set to modified tells Ansible to save the configuration only if changes were made. This prevents unnecessary configuration writes and follows idempotent principles. The second section shows a Terraform configuration for AWS VPN. While AWS VPN Gateway does not support MSS clamping directly, you can use Terraform to document the required on-premises configuration and output reminders. The AWS_VPN_connection resource creates the VPN connection. The tags include an MSS_requirement field with the value 1379. This documents the MSS requirement for anyone managing the infrastructure. The output block provides a reminder message that MSS clamping must be configured on premises. The third section shows a Python script using the NetMiko library for network automation. NetMiko is particularly useful for devices that lack native automation support. The script connects to a device, sends configuration commands including the MSS adjustment, and then disconnects. The device dictionary contains connection parameters including device type, host, username, and password. The config_commands list contains the commands to execute, including entering interface configuration and setting the MSS value. The script uses the send_config_set method to apply these commands. These automation approaches ensure MSS configuration remains consistent as your network grows and changes. Include MSS settings in your infrastructure as a code repositories and apply them through your standard deployment pipelines. Best Practices Summary. Let me summarize the key best practices for TCP MSS adjustment based on everything we have covered in this presentation. Following these guidelines will help you implement MSS clamping effectively and avoid common pitfalls. The diagram organizes best practices into 4 categories: planning, configuration, verification, and maintenance. Let me discuss each area. In the planning phase, you should document all tunnel types and their overhead in your network. Create a network diagram that shows where encapsulation occurs and calculate the required MSS for each path. Do not guess at values. Measure or calculate them based on actual protocol overhead. Consider the worst-case path when multiple encapsulations might stack. For configuration best practices, always apply MSS clamping at tunnel entry points where packets will be encapsulated. Configure both directions of tunnels because traffic flows both ways. Use conservative MSS values when you are uncertain. It is better to be 20 bytes too low than 1 byte too high. Document your MSS configurations in configuration management systems so the reasoning is preserved. Verification is critical after any MSS configuration changes. Test with actual traffic, not just ping tests. Transfer large files and verify they complete successfully. Use packet captures to confirm MSS values are being modified as expected. Verify from multiple source locations to ensure all paths are covered. Test both directions of each connection. Maintenance ensures your MSS configuration remains correct over time. Review MSS settings when adding new tunnels or changing encapsulation. Include MSS verification in change management procedures. Monitor for fragmentation, which indicates MSS may need adjustment. Update MSS values when migrating to new platforms or cloud providers that may have different overhead. Additional recommendations include avoiding reliance on PMTUD alone since it fails too frequently in production networks. Implement MSS clamping proactively rather than waiting for problems. Standardize on common MSS values where possible to simplify management. When in doubt, use 1400 as a safe default that accommodates most tunnel types. Remember that MSS clamping has negligible performance impact but provides significant reliability benefits. The minor reduction in per-packet efficiency is far outweighed by avoiding fragmentation and black hole issues. Conclusion and key takeaways. We have covered the complete topic of TCP MSS adjustment from fundamental concepts through advanced implementation scenarios. Let me summarize the key takeaways that you should remember from this presentation. The first key takeaway is understanding the relationship between MTU and MSS. MTU defines the maximum packet size at layer 3, while MSS defines the maximum TCP payload size. MSS equals MTU minus the IP and TCP headers, giving 1460 bytes for standard Ethernet. Any encapsulation reduces the effective MTU and must be reflected in a reduced MSS. The second takeaway is recognizing when MSS issues occur. Symptoms include connections that establish but stall during data transfer, small requests succeeding while large transfers fail, and applications that work on local networks but fail across VPNs. These patterns should immediately trigger investigation of MSS and MTU. The third takeaway is understanding why PMTUD fails. Path MTU discovery relies on ICMP fragmentation needed messages that are frequently blocked by firewalls. This creates black holes where large packets disappear without any feedback to the sender. You cannot rely on PMTUD in production networks. The fourth takeaway is the solution: TCP MSS clamping. By reducing the MSS advertised during TCP handshake, you ensure packets are sized appropriately before they enter tunnels. This is transparent to endpoints and eliminates dependency on PMTUD. The fifth takeaway covers implementation. Every major platform supports MSS clamping. Cisco uses IPTCP adjust MSS on interfaces. Linux uses IP tables with the TCP MSS target. Palo Alto uses zone protection profiles. FortiGate configures MSS on policies or VPN interfaces. Cloud providers require on-premises MSS configuration. The sixth takeaway is to use appropriate values. Standard VPN tunnels typically need MSS around 1360 to 1400. AWS VPN recommends 1379. Azure and GCP recommend 1350 to 1360. IP version 6 requires 20 bytes less than IP version 4 equivalents. When uncertain, use 1400 as a safe default. The final takeaway is that prevention is better than troubleshooting. Implement MSS clamping proactively on all tunnel interfaces. The minimal performance impact is far outweighed by the reliability benefits. Include MSS configuration in your standard deployment procedures and automation. Thank you for your attendance. Please consider subscribing to the channel and liking this video.